Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, it's my great pleasure today to welcome Professor Hao Jiang from Boston College here to give a talk. The title of the talk is Efficient Global Methods for Robust Computer Vision. Hao actually had 2 PhDs, one in Simon Fraser University in computer science and a PhD degree in EE from Tsinghua University in China. Before he joined Boston College, he had worked at the University of British Columbia as a postdoctoral research fellow, and also MSR Asia as an associate researcher. Without further ado, please.
Thanks. All right. Okay, so today I'm going to talk about something I did in the past several years. So I'm going to focus on some efficient methods using global methods. Okay, so the first, let's talk about the motivation. So why we need these kind of global methods. So in computer vision, there are many problems that we need this kind of global model instead of local things. So for example, this is a very simple kind of application that we want to match some templates in the target image. So on the template, usually we have a lot of feature points. And on the target image, you have many, many possible candidates. So on this, all these feature points, usually they not only we require them to have good local feature matching, we also need them to have some kind of global constraints. For example, we need them to match, they have the uniform transformation. So they have the global scale and the global rotation to be kind of consistent during the matching. So that's something that we need to make sure that the matching to be robust. So that's very important. And not only for matching, in fact, there are many other models. We need this kind of global thing instead of local models. Okay, unfortunately, the global model is very hard to deal with because this kind of global constraint introduce a lot of things that are hard to deal with. So in fact, there are a lot of previous methods already try to deal with this kind of situation. So for example, we can use like the ransack, we can use half transform to deal with this kind of global models. But unfortunately, a lot of models, the previous ones, they have some kind of issue. One is some of them is not fast enough for the real applications. And some others have to deal with some kind of local search instead of doing some kind of real global search. And that's going to affect the quality of the algorithm. So we're going to use some other different kind of way to solve the global models. So here's our approach. So because in computer vision, we can usually we can formulate the problem into some kind of energy minimization problem. So we have some kind of criterion to tell us. So this kind of, for example, this kind of matching is good or not. But fortunately, in computer vision, we don't really need this model to be very accurate. So we can do something to manipulate the model itself so that the model has some kind of interesting property we can use. And to make it not only reflect the trend of the problem, but also we can make it easier to solve. So that's basically our approach. So we manipulate the formulation, and so that we can look at the formulation, look at the problem, and we find some kind of structure so that we can solve the problem very efficiently. In fact, we can use this kind of idea to solve different problems. So like we can do matching, we can do object detection, and we can do human pose, and we can do like multiple object tracking, and even segmentation. So I'm going to talk about some of these applications in this talk. Okay, so let's talk about the first method we propose. The first one we called, there's a name we call it, is the lower convex Hall method. So I'm going to use one application to explain how this thing works. But in fact, this method is quite general, so you can use it for other problems if the problem formulation has the similar kind of property in there. but object matching is a very natural application for this. So let's use this as an example. So here's the setting for the object matching applications. So on the top row, you can see there's a B in there, and the model basically is a mesh on the B. So you have feature points, and also between the feature points, you have all these pairwise constraints in there. So it's like you have the nodes and you have the edges to indicate how these feature points relate to each other. The goal basically, we want to find the correspondence of all these feature points from this template to the target image. So like this is the target image, and the matching itself, basically you find all the correspondence, and you can see this B is different from that one because there's a rotation, there's maybe a scaling changes, there could be deformation. So it's a hard problem to deal with. So we have to somehow find the correct matching and also deal with this kind of scale rotation, this kind of everything together.
How do you generate the mesh?
I'm sorry?
How do you generate this mesh?
Okay, so this one basically is because we find the point-to-point correspondence, basically you transform that mesh to here. So use the same kind of pairwise.
How do you get the original mesh? How do you
That one is we use the Delaunay triangulation.
Okay.
So you can do some other things, but Delaunay triangulation is an easy way to get a mesh. So basically, this is a kind of mesh matching problem. You have a mesh, and you want to find the correspondence of all the nodes to the target in the target image. So that's the basic problem. And the feature itself is in fact not very important. So you can use like a sieved feature, you can use shape context, you can different things. So I'm going to show you some examples to use different features, but the formulation is very similar. Okay, let's do some kind of formulation now. So we're going to do this using this energy minimization framework. So basically, we define some kind of criterion. So which matching is good, which matching is bad. So we're going to use a number. So this number basically tells you, okay, if you do this, and this is a good one. So for example, this is the template in here, and this is the target. So the good matching should have each of the feature points should have low cost itself. So that's basically the first term in there. So if you find a good matching, so the first term, so this point-to-point matching should have very low cost. And also, we should maintain this kind of the global structure of this model. So the global structure is, they have all the points should rotate consistently. So there should be some kind of consistent rotation for all these points. And also all the points should scale consistently. So there's another term. So that's the reason we have the second term in there. And we have two parameters we need to estimate in here. So F basically estimate all these kind of point-to-point correspondence. And this S in there, small s, that's the scale. And there's a rotation matrix R.
So you just mentioned the feature doesn't matter. You just select any other feature to do global. But in some way, you could also select a little bit like holistic features to speed up for a global matching, right? For you to have a good initial condition to start with.
I mean, feature is important, but this formulation is independent of the feature itself. So you can use like a sieved feature, you can use some other features. Of course, some feature is good, it's better than others. But the whole thing is basically the same. I mean, features are very important. If you use good features, you get better results. But if you use a kind of weaker features, the result may be a little bit worse. But I mean, the whole thing is the same thing. You can use all these kind of things. If you can get a cost, so for this point, if you can find a cost to match the target point, that's all we want. So no matter what kind of feature you use to get this kind of matching cost. So, okay, so the second term is, we call it the pairwise consistency term. So basically, we want this kind of all the pairs of this kind of vector to rotate. You can see there's a rotation there, and the scaling, they should be consistent. So all the pairs, so this PQ and these two pair, they should have exactly the same, almost similar. I mean, they don't have to be exactly the same, but they have to be really similar, this kind of scaling, this kind of rotation.
So you're assuming effectively in-plane rotations.
Right.
Yeah.
So if there's out-plane rotation, it's going to be deformation, basically. But this model, in fact, allows this kind of deformation, a little bit, not much. So
Why not use the alpha constraint?
In fact, there's some other. So you can see that there's an S in there, there's an I in there. So if you, in fact, an easy way is that you put R and S together. So as you said, you can use alpha transformation probably. And in fact, you can use like general, like a linear transform in there. But the problem is, if you do that, in fact, the result has a bias to match the single point. So because if you match to a single point, the second term will have 0 energy in there, and that's very small. So we don't want that happen. So that's the reason we split R and S into two different places, and then we can kind of avoid this kind of situation. Basically, we scale the target, and instead of scaling the template. And that, in fact, makes the model much more complex to deal with. But you have to do this. All right. So
How does your second term cope with the, let's say, disappearance of certain features and reappearance of certain features, because they are not exactly 2D objects, they're 3D?
okay. So in fact, we don't. I mean, if there are some new features come out, that's fine. So we only match the feature you see on the template. And if there's some feature kind of disappear, that's fine too. I mean, there's some feature we don't really allow this one feature match to a single location. So for example, some object shrinks to some smaller size. So maybe 2 feature points goes to a single point. So in fact, we allow this kind of situation to appear. So that's probably not really a problem. I mean, the outliers is a problem. I'm going to show some videos. If you put a hand before some object, occlude something, that's going to be an issue. But you still can match the target if there's some other kind of thing helps you. Okay, so so we're going to use this objective function. So this is in fact not the hard part. If you just write this out, and hopefully we can solve it. But unfortunately, this thing is really hard to solve because there's something that's not very desirable in here. The thing is not linear model in here. So it's quite a nonlinear thing. In fact, it's a quadratic thing. So all the ovals I put in there, they are something like a quadratic term in here. You can see this s times x, because s and x, this capital X, they're both variables. Okay, let me explain a little bit of this formulation. In fact, this formulation is exactly the same as the previous one. The only difference is that we use the matrix notations to represent everything, to make it simpler, so that we can take a kind of closer look at this thing, and also we can manipulate it a little bit easier. So this X basically is a assignment matrix. So because we want to find the correspondence from each feature point on the template to the target points. So this X basically is, for example, you have n points on the template, n points on the target, is n by n matrix. And you have each of the element on this matrix is 0, 1. So if you have a matching for 1 point to some feature point, target feature point, there's a 1 in there. And everything else will be 0. So basically that's a 0, 1 matrix for this capital X. And this capital C in there, that's the cost matrix. So if you do this trace, this transpose of C times X, I mean, there's a simple trick of computing all the corresponding kind of product, and you can get the overall kind of matching cost for the matching. Some other things is already there. So for example, this rotation matrix R, and this is S is the scaling factor in there. And this M and this T here, they are basically just you stack all the template points together, you get this M matrix. And you stack everything of the target points there, this is the T matrix. And this E introduced this kind of, you can see this in here is you have a subtraction in there of these pairs. So this is basically this E's matrix introduced this kind of effect. So for all the pairs, we somehow introduce a minus thing.
So E effectively turns on and off certain rows then, correct?
Turns on, in fact, for all the edges in there. If there's an edge between 2 points, you somehow.
M is sort of, rep-matted versions of all the points, correct? Because you'll have for every single point, you need to encode every single possible combination of all the template points and all the matching points. So E is effectively going to turn on and off those points such that only a single pairwise term is active at a time, right?
Right. Yeah, something like that. Yeah. So as you can see, so this constraint basically the first one is we have to make sure that this assignment matrix has a single one on each row, because each template point only match to a single target point. You don't want a single feature point match to 2 of them. So that's a kind of constraint in there. And also it's a binary matrix in here. And also this R has a kind of orthonormal constraint is a quadratic constraint. So you can see this thing is nonlinear on the objective function, also nonlinear on the constraints. So it's not very easy to deal with. Also, it's an integer optimization problem. So we have to do something so that we can easily solve this. So the idea basically we somehow turn everything into linear, and hopefully, even though probably it's an approximation, but because it's linear, it's easier to deal with. So that's basically the idea. So we need to do a bunch of things to somehow linearize it. So the first thing we need to do is we somehow linearize this absolute value term. So basically it's the term in this brown, this oval in there. So that term, in fact, that's a kind of standard linear programming trick. So if you want to minimize something in this absolute value, you can introduce two auxiliary variables, y and z. You just minimize y plus z in the objective function, and introduce y minus z, let it equals x in the constraint. And if you make sure this y and z they are non-negative, and in fact, it's equivalent to minimize the original this thing, because y and z, one of them has to be 0. And in fact, this y plus z has to be the absolute value of x. So, and in here, we don't really have this scalar y and z in here, but we have some, you can use the similar trick, but use like two matrices. Two matrices, one is capital Y, the other one is capital Z, and you do the same thing, basically. And you can replace everything if you want to put into the absolute value term, just let it subtract the difference of this Y and Z, and it equals that term, and you put this Y plus Z into the objective function, and you can realize this kind of absolute value minimization problem.
For this matrix, how many new constraints do you add?
So in fact, let me see. In fact, how many pairs of this kind of pairs of the points? That's in fact how many this kind of thing you have to put in there. So
it's m by t then.
Yeah, there are quite a lot of constraints you have to put in there. So I'm going to talk about how we can deal with this kind of thing. So the whole thing is going to be huge. Yeah. So you have to do something to solve this.
Sure.
So this is only solves a partial of the problem, because even though this thing it's not in the objective function, but it's still here. So it's still kind of, we have to somehow deal with this kind of scale thing, because that's s times x, that's a quadratic term. So for this, to turn this thing into some linear function, so what we do is, so instead of doing this kind of matching a point on the template to some target point, what we do is we match the point from template to target at some specific scale. So essentially, we introduce another dimension for the matching, a scale. So in here, you can see, basically, we extend the matching to originally assigned matrix is like 2D. So basically, you put another dimension that's a scale in there, so that you have a bunch of layers in there. And in fact, you want to find the matching and also that scale at the same time. And if you collapse everything together, and it's going to get the original x. So this XL basically a bunch of slices of this 3D thing. So basically, the original thing is nonlinear, but if you increase the dimensionality, and hopefully we can turn it into something linear. So that's the basic idea in here.
Do you add a constraint then that effectively only one scale can be selected at a time?
Right. Yeah. Okay. Yeah. We need that kind of thing. And so after we do that, basically we just do this. This is approximation. This SL is a bunch of quantized scale in there. But even though this is a contact thing, because finally we're going to relax this thing into some kind of continuous variable. So in fact, you got a lot of things in the middle. So you got a continuous scale in the end. So that's another big concern, even though we roughly kind of quantize this scale in here. So after we do this, and we turn this into a bunch of linear thing in here. But the variable is not x anymore, it becomes this XL, basically slices of this 3D assignment matrix in there. And also, as you said, we need this to make sure all this matching, each point matching needs the same scale S. So this is S in there. So now we have turned most of the things into linear. There's only one thing left, is this rotation matrix. What we do here is we do approximation, using some kind of use a square to replace a circle. So if you somehow quantize this, quantify this rotation matrix using two variables, u and v. So what you get is basically the original thing is u squared plus v squared equals 1. That's a circle if you plot it on the using graph. And so this circle thing apparently is not convex, right? I mean, if it's a disk, it's a convex thing, but it's a circle, you only have the boundary, it's not convex at all. So what we do is, okay, let's use this somehow approximate using this rectangle. This rectangle essentially is basically the u absolute value plus v absolute value equals 1. So it's approximate is the u squared plus v squared equals 1 thing. And unfortunately, this square itself is still non-convex, but it's easy to fix. We just need to break this square into 4 line segments, and each of the line segment is a convex thing. So now we can, we introduce, we break the original problem into 4 smaller sub-problems, but fortunately it's not too many, just 4 of them. So we can still solve them quite efficiently. So okay, after all these steps, in fact, we turn this into a linear thing. So the thing I want to show it in here is, even though it looks a little bit more complex, but in fact it's much simpler than the original problem, because the object function and this constraint, they become all linear. So you can just throw this into some kind of linear solver, and hopefully you can solve it quite fast. But in the real situation, this is not very useful. The reason is that it's going to be huge linear programming here. And if you directly solve it using a solver, it's going to take a long time, take forever. And also, maybe the problem is it's too big and you cannot fit into the memory of your computer at all. So you have to do something to solve this thing and to make it very fast. So what we do is, we look at this thing closely, and we found there are some properties in there we can use. We don't really need to solve the original problem. In fact, we can solve this using some kind of simplified version of the problem. And this simplified version, in fact, has exactly the same solution as the previous one. So the property is, in fact, is the lower convex Hall property we're going to use. So that's the reason this kind of method is called the lower convex Hall method. Okay, what I showed here is a matching cost for 1 point. So if you use one feature point on the template, you match all the feature points on the target image, and each of them you have a cost. So this bar in here shows the cost. And so when you build the linear optimization problem in there, so originally you have to use all of this, right? So you're going to have lots of variables in there. But fortunately, we don't really need all of them. So because we linearize it, after we linearize it and you relax it into some kind of linear program, and the linearization and the relaxation itself, in fact, turns that thing into a surface. And this surface essentially is a lower convex Hall of all that points. It's the tightest bow to support all the points. It's like you use a rubber band to support all these points from below. And only the supporting points, the lowest supporting points, they are important. They are on this surface. Everything else is above the surface. In fact, they are useless. You can throw away everything above and just keep everything, the supporting points.
Sorry, I missed that. Why are they useless?
Because the linear programming itself is, in fact, is just to use this surface to represent everything. I mean, this is a linear program. If you don't, the original x is a binary, right? But we don't really want to solve this binary integer program. Because it's generally this binary linear program is NP hard. You don't really want to solve that kind of thing. So we turn that x into something like between 0, 1.
Yeah.
0 and 1.
Have you tried, some cutting plane?
Oh, it's really slow. Yeah, we try that. It's really, really slow. So it's not solvable. So that's the reason we want to kind of linearize it and relax it, and to make it easier to solve. So the relaxation, in fact, you don't solve the original problem. In fact, you use this surface in there. You can prove that is just the case. And so that means we don't really need to keep all these variables in there. We can throw away all the variables, just keep something we call the effective variables in there. So there's an example in here. So for example, there's a surface in there. And if you don't do anything, don't do any simplification, you're going to have like 2,500 variables to represent the optimization. But if you do this lower convex Hall using this trick, you can see the vertices in there, only these blue points in there. There are very few. There are only like 19 of them. So that means if you do this, use this trick, you can just use 19 variables to represent the problem and itself. So it's going to become much smaller, and it means you can solve this thing really, really fast. And this one shows, in fact, if you increase the point, the number of, in fact, how many target candidates, you can have how many these kind of points in there originally. And if you use lower convex Hall, you can see that, so this one, in fact, only like 28 of them is useful. And if you increase this thing to like 1 million of them in here, and there are 1,000 effective things. So, I mean, even the target kind of candidates, the number increase very fast. It seems that the effective target won't increase very fast. So probably, so you can still deal with this kind of scale of the problem without any problem. So that means we can deal with a lot of target feature candidates, and we can do this kind of thing very fast, efficiently. So without worrying about the complexity is too high. And also the good thing is the result is exactly the same as the previous one, and you don't lose anything when doing this. So here's an example that shows how this thing works. So what I'm going to show is a very tall example. So you have only like 4 feature points in there, and that's the graph we use. And this is a target image. There are a bunch of, I didn't show the original image, but that's only all the feature points, the yellow points in there. And if you do the first matching using this relaxation, what you get is something like that. So in here, this blue dots in there, that's the true point. And the circle in there is what you get. So you can see that the first matching is in fact not very accurate. The reason this thing is, but it's close, it's not very accurate. The reason we do the regulation, we didn't solve the original problem. So we need to do something to make this more accurate. What we do is that we use something we call the trust region shrinking method. So basically, after you do the first matching, you don't stop it there. You shrink your trust region because you know that the target may be around that point you find. And you make your trust region a bit smaller, and you redo everything, and then you can make your result much better. So this is, in fact, shows how this kind of trust region shrinking works. Let me show it again. So after you do this thing, so that rectangle basically is the region you trust, and the trust region can become smaller and smaller, and finally you can have much better matching.
How do you determine that trust region?
Oh, so now we basically just use a rectangle around that thing. So you can center that thing around. You can use some other kind of criteria. In fact, it's not quite critical. We try different ways, so and it works similarly.
This trust region is a region in which you're only going to use possible feature matching candidates.
Right. So basically, you throw away everything kind of outside of the region. So that in fact makes you convex Hall kind of more accurate. So because the region is smaller, and your convex Hall become more kind of similar to the original surface. So that's another reason it's going to become more accurate.
So you're solving this as an LP then, correct?
Right.
So how do you resolve the fractional solutions?
Okay, so we don't do rounding in here. So basically, we just linear combine all these target points. So each of them has a floating weight, right? So you just linear combine them and get the target position. So that's another good thing. We don't really need to kind of tweak the threshold in there. So here's another example. Use a different kind of feature. They use shape context. So that's the template in there, and there's a fish. You can see it's embedded in a lot of cluttering here. So after the first matching, and in fact it's not so good. It's just roughly there. But if you do this again, so when the region becomes much smaller, and you get better and better matching, and finally you get the target. In fact, this a lot of about almost 100% of cluttering there is you can still find the matching quite well. And here's another example that shows we use the shape context instead of we use sift instead of shape context. So this is the template we use, and this is the target image. So we use all the sift features in the target image. So we use a 0 threshold in there, so you can see everywhere there's a sift feature. And then we do the matching, the first one, and then you keep on doing this kind of trust region shrinkage and solve this kind of linear program again and again. And finally, you can find the matching quite well. And you can see that the original one is smaller, right? And the target is bigger. So we can deal with this kind of scale thing and the rotation thing at the same time. So there are some videos that shows how this thing works for some videos. So not only we can deal with the rotation, the scale, we can also deal with like the butterfly there. There's some kind of deformation in there. Also this magazine in there. Also there's a deformation in there. So we can deal with all these things together. And the good thing about this, you don't really need to worry about which feature is good, which feature is bad. Basically, you just select as many features as possible. Let the algorithm decide which one we should use. And so that's a good thing, especially when there's some occlusion. So at the end of that video, so in fact, it's not in here. It's in my website. There's another video. I put the hand before the book or something. So if you're interested, you can go to my website to look at that video. So so there's some, it's not totally accurate in here because we don't use any motion continuous thing. So you can see there's sometimes the matching is suddenly there's a wrong matching in there. But I mean, it's a good and bad. Sometimes you hope that this kind of the matching error won't propagate. So this is the way you do. You just match each of single frames. Okay, so we do some comparison. So in here, we compare with some kind of very fast method using the local search. So it's the SEM, iterative conditional mode. So this row basically is that method's result. You can see it doesn't work really well because the feature, if it's weak sometimes, and it won't find the target, right target. But the proposed method works very well for these videos. And the interesting part is that not only this proposed method has the better result, and also it's in fact faster than this kind of greedy method. And the reason we can do this very fast is we use this special structure of the problem. We call the lower convex Hall property. And so this in fact shows is a fraction of the time of the using ICM. And also this the performance is like several times better than this greedy thing. So.
Two questions.
Okay.
So what's the absolute running time per frame?
Okay, so the typical time is if you have like 100 feature points on a target, each iteration probably a second, something like that. So usually like 5 iterations is good enough.
That's several seconds per image.
Yeah.
Okay.
But if you use like fewer template points, it could become much faster. Okay. So it's quite sensitive to the number of template points, but not very sensitive how many target points you have. So that's the good thing about it. So if you have just tens of 20 feature points or 50 feature points, something, it could be much faster. It could be real time.
And how are you evaluating the accuracy? Like how is the accuracy measured here?
Oh, okay. So for here, in fact, we don't really have the ground truth. So basically, we just this is a visual inspection for this. And there are some, when we do the point matching, so I show there's a result in here. So we use like a point set. So we know the ground truth. We know the target where they are. So this is like, we just do like the distance, average distance or something. And so this is in fact an arrow histogram. So to show that, I mean, on the left-hand side is this kind of the small arrow, and on the right-hand side, the big arrow. So basically, it's a histogram of all these the matching arrows. So the good algorithm should have everything on the left-hand side and the very flat tail on the right-hand side. And this black curve basically is ours. So we compare our method with some other methods like the thin plate spline method, and it's the TPS, and there's a graph, spectral graph method or something. So, and this method in fact works quite well when when there are not many noises in the image. But if you have a lot of clutter kind of thing in there, and there's kind of breaks very quickly. But the proposed method still works well in that case.
Does your template adapt every frame, or is first frame is template?
Oh, it doesn't have to be the first frame. You can randomly choose one. So if there's an object like a fish or something, no, it doesn't change. So
So if the object has deformation or occlusion, like then you have a problem.
I mean, in fact, I tried to put a hand in front of the book. The hand basically occludes half of the book, but it still works in that case. The reason it works is there's some good features in there, and the bad part, I mean outliers. In fact, because there is no target in there, so the template point is going to match everywhere has similar cost. So essentially, that part of the feature won't kind of count when you do the optimization. So the algorithm basically selects a good feature automatically when you do this kind of. But if you have more than half of the occlusion, you may have trouble in there. But in our experiment, so half of the occlusion seems okay. It won't affect the result very much. Okay, so we also compare with some robust method like ransack. So ransack, in fact, works quite well when the feature is good. It's not, I mean, when it's not too bad. So in here, so this pair, in fact, the feature is pretty weak. The reason is you can see that this fur has similar appearance everywhere. So ransack won't find the good hypotheses. In fact, almost all the hypotheses is wrong. No matter how many tiles you try, it's wrong. But our method basically relies on all the features in there. So it doesn't depend on the kind of the good features itself. So even though, I mean, it's the second best feature, if you put them together, it has the lower matching cost, and we're going to select that. But the ransack won't have that kind of result. So that's the first method. And in fact, there's still some method still some problems we didn't deal with in the first method. So that's the reason we're going to introduce another one we call the decomposition methods. So in here, basically, we want to solve a few extra problems that we didn't do. I'm going to still use this matching problem as a example, but I mean this formulation also is quite general. You can use it if the structure fits some other problem. You can use the similar method to deal with. Okay, the problem that we didn't quite solve in the previous version is that because we somehow have to quantize the scale, so we need to know at least the range of the scale changes from the template to the target. So for example, it's like within 2 times. So like half of the size to like 2 times bigger than that. But unfortunately, sometimes you don't really know how big the scale could change. I mean, if you download the image from the internet, the size can become very different from your template. So how do you deal with that? And probably you don't really want to try each of the scale because it's going to become really slow if you quantize very fine. And also maybe you have to try all the rotations that make things even worse. So, so the question is there's a way that we don't really need to know the scale and we still can do the matching? Is that possible? In fact, it's possible. I'm going to show you one way to do that. And also another thing is about the model. In fact, in the previous model, we have to use all the pairwise constraint need to use something like the convex norm. So basically, we use L1 norm in there. But sometimes we want to use some kind of general pairwise constraints. And how do we handle that kind of case? And also, because our model is like, it's not a tree at all. So if it's a tree, basically you can do like dynamic programming, allow this kind of, for example, this blue part, the blue edges. If it's a tree itself, you can use very complex constraint, use dynamic programming. But if it's not usable. And so what we do is that, okay, let's do some kind of compromise in there. We still use a tree but this time we use it as a skeleton in there. And we introduce some kind of extra edges in there. It's a dotted thing in there. That's basically the weak edges. The weak edges is a special thing. They are somehow can be represented as the linear constraints. So basically, this is a blue thing, the arbitrary thing. They could be anything. And the skeleton can be very complex constraints. But everything else you put in there has to be something linear. And so this model, in fact, is not a tree anymore. It's a loopy graph. But it's not a totally generic loopy graph. It's something we call the linearly augmented tree. And interesting, this thing is, even though it's not a complete general loopy graph, but it has the good thing about the good features about this loopy graph. You can introduce many constraints that tree does not have. And at the same time, so we have a good algorithm to solve this using a bunch of tree algorithm to solve it. So you have both sides of the good things. You have the property of the non-tree model, and also you can solve it very efficiently using tree methods. So that's the reason we want to use this kind of linear augmented tree thing. Okay, so we still need to do a little bit kind of formulation, but this is very similar to the previous one. So with the objective function is, we also have this unary term. So basically, for each feature point you want to find the low cost target point. And also the second term, we also need this kind of the spatial kind of consistency term. So we need everything rotate with a similar angle, and they have the scaling has a kind of a similar angle, something. And in here, okay, so this is, we can also use this kind of matrix notation to represent everything. So this is second term in here. So the difference of this, the second term with from the previous model is that in here we only constrain everything on the tree. So we have a skeleton tree in there. So basically, if you constrain the tree to rotate consistently and the scale consistently, in fact, the whole model probably has that property too. So in fact, this is important. If you don't do this, and that model is going to fail. So we only apply this kind of consistency constraint on the tree edge. So this thing turns out can also be represented using some kind of matrix notations. I mean, if you want to know, I mean, look at the details. I mean, the paper has a little bit more, but in fact, there's not much more in there. It's just the notations and the.
Well, can I try to rephrase what you're saying?
Okay.
You're saying, in order to cut down the number of constraints and costs, instead of ensuring that the rotation and scale is consistent among every single edge,
right,
just select a subset. And in this case, that subset happens to be a tree,
right,
such that the constraints hold, et cetera, et cetera.
Right. In fact, we do this. There's another. I'm going to show you. There's a later slide to show the structure of the thing. So in fact, that helps that kind of structure to appear.
Well, so does it have to be a tree necessarily, or put another way, why a tree and not random edges, let's say?
Okay. So okay. In fact, it's become a little bit clearer after.
Okay.
So let's wait a little bit, and I'm going to show you there's a structure in there. So in here, basically, we want to make sure all these tree edges they have the same scaling. So this term basically the same scaling. So with this S0 in there, and also we have the same kind of rotation. There's a theta in there, but the trick in here is that we don't make sure all the edges rotate with the same theta. We make sure they have the same cosine and cosine theta. The reason we do this is that because the angle when you rotate across 0, it flicks back to like a 360. That's very hard to deal with. So but if you do like sine and cosine, you don't have this kind of trouble. So even though you have two more kind of matrix in there, but it's fine. So basically, this U0 is something like a target cosine that theta, and this V0 is the target sine theta in there. And we try to minimize everything in here so that make sure the whole thing kind of doing something consistent. So the last, I mean, you can add some other terms too. I mean, there could be some kind of a global thing to make sure there's some other, like the area constraint to work or something. I mean, if there's something linear, you can add them in there. It won't affect the whole model. Okay, so in fact, this is basically the structure of the whole thing. So if we do everything kind of we talked about before, you're going to have some very special structure in here. So you have an objective function, you have the constraint, and the constraint in fact, there are two parts in the constraints. One part is easy ones, and there are hard constraints to add on this kind of easy one. Okay, the easy ones, in fact, they are the tree constraints, everything on the tree. And the hard ones is something that's put on top of this tree. So this is the linear. And so this part, I mean, if you remove this part, so basically the whole thing is the tree optimization problem. It's optimization, but you can use dynamic programming to solve it if you remove these hard constraints. But if you put them back, it's something kind of, you put something into the tree formulation. So that's, in fact, makes the thing a little bit harder to deal with. But it's not too much different from a tree. What we need to do is probably somehow, if we figure out the tree solution, we can try to make this thing works. And then probably we can get a solution much faster than solving the whole thing. So that's basically the idea. I mean, what we did everything before, basically we want to make this kind of structure to appear. So, all right, okay, so let me kind of briefly illustrate how this thing can be done faster using these kind of tree solutions. So in fact, the basic idea is, let's assume that you have a bunch of, you have all the tree solutions. So basically you remove the hard part, and if you can somehow magically get all the tree solutions in there, so we represent them using this kind of the green dots in there. And then because you removed hard constraints and the feasible region in fact become bigger, so that's the reason I draw a bigger area in there. And the real solution probably is only in that triangle. And the red dot is the real kind of global optimum solution. And as you can see that, you can always use all these green dots to do a linear combination and represent that green dots. And hopefully this can be done a little bit easier than you directly solve the hard problem, because these green dots may be easier to get. I mean, even though this thing won't work by itself, because you cannot afford to get all these green dots in there. But fortunately, we don't really need to get all of them at the same time. What we do is, there is some method which is called the column generation. It's in fact is a method in this Danzig-Wolff decomposition. So in fact it's a quite old method. It's like a 20 years, 30 years ago method. In fact, probably even older than that. But that method, in fact, tells us how to deal with this kind of problem. So if you know the solution for this kind of simple problem, you can do a little bit more and to make it work for this kind of a little bit hard problem. And the idea is, in fact, you can use like a bunch of proposals as to start from. So for example, you do like 2 dots instead of all the green dots. So this, and you do a linear combination. You find the best thing for the linear combination of these 2 dots. And you find one kind of okay solution, not the best. So that's basically the red dots to make it satisfy these hard constraints. So after you find that, so we can introduce more proposals. So let's say, okay, so probably we should introduce another one in there. And in here, in fact, you already get the final solution if you do a linear combination of using these only 3 of them. So the procedure of this column generation is, in fact, how you can introduce more proposals to make sure that you always improve your result. There's a very systematic method to do that. And so this thing is going to, in fact, is in our problem. So you don't really need to solve the sub-problem using any kind of a linear program or something. Basically, what you do is a tree. Okay, the sub-problem is tree. You just do dynamic programming. It's really fast. And after you solve that, you can solve another small linear program to generate new proposals. And after a bunch of iterations, you can find the result much quickly than directly solve it. So that's kind of the basic idea of this method.
So for various proposals, you just randomly try, or you have a little bit guidance about from the mesh?
You don't randomly try the proposals. In fact, there's a systematic method to tell how you choose the next proposal. So, I mean, it's a part of this Danzig-Wolff decomposition method.
So can you elaborate briefly, like what's the insights for selecting proposals?
The proposal, basically, you want you want to select the one if you introduce it to reduce your objective function the most. So that's the proposal you want to select. So in fact, in that case, you want to do that, you solve a very small linear program in there, and after you do that, you can compute the proposal instead of randomly choose one.
So does that proposal also has a little bit linkage with the structure of the mesh? I mean, that's something I think is a bit key. For example, if it's a human, perhaps those points are more lying on the skeletal of the human. And for your bear or something, maybe there are a few anchor points. If you happen to collide into those anchor points, your you got the decreased cost the most in that? Is there any analysis of linkage? I'm just
you mean the structure, whether the structure is going to affect
the structure of the mesh or of the geometry?
Okay, I think that's a different problem. It's I mean, the structure definitely, I mean, if you choose a different structure, it's going to affect your solution. I mean, some structure is better than others. But in here, basically, we just do Delaunay triangulation, get a kind of planar graph in there. And it works okay for this kind of most rigid object. I mean, if you do like articulated object, this kind of graph may be not very good. You should choose like some other kind of graph in there. But I mean, the optimization method they're all the same. It doesn't matter what kind of graph you use. So you can use like manually choose some kind of better graph in there. So for example, if you have articulated part, maybe you don't really want a linkage in here. You want the linkage, everything kind of inside the area. So, but I mean, it won't affect the method itself.
Yeah, the reason I'm saying that is one of the possible things you could do is for like segmentation, that like in computer vision. So you could have form a loop. You could do a random matching using your method. But meanwhile, once you establish this kind of correspondence, you roughly know the structure of the object. And then that structure perhaps could go back to influence your matching in some more.
Okay. So I mean, you can automatically generate the structure to help the matching or something.
Something like that.
Okay.
I was just wondering if.
Okay, that's a good idea.
So
So probably can do something in the future along that direction. Okay. All right. So that's basically the rough idea of the. I mean, I didn't talk about the very details of how this proposal is selected, how the iteration works. But basically, that's some kind of the basic high-level thing. I mean, there are a lot of details in that paper about how that could be selected. In fact, it's a quite structured way. There's no guess, and there's a kind of randomly selection in there. So everything is just determined. You can just follow that structure, and I mean, procedure just go do iterations. So the example I show here, basically how this thing kind of looks like if you do these kind of iterations. So for example, there's a template image. What we want to do here is we want to match the regions. So for example, if you run some kind of superpixel method on this image, you're going to get a lot of this kind of the regions, that's the superpixels. And because this kind of superpixel method usually works really fast, so that's something probably is, also there are very few superpixels in here. So if you use that as a feature to match the target, so we can do probably like real-time matching, even though probably not very accurate, but we can localize the object very quickly, and we know the rough pose or something. So that's basically the motivation we want to use this kind of feature. And we use a very simple graph. The tree in here is the star, that all the red edges in there. And we only have like 10 regions in here, so not many regions. And this is the target. As you can see that this guy, even though it's the same object, in fact, the regions a little bit different. So each time you run this kind of superpixel algorithm on the same object, you'll probably get some kind of not exactly the same, but maybe some parts the same, roughly the same. So that's, in fact, is a quite challenging problem, how you can deal with kind of unstable kind of regions matching. So here's an example that shows the first iteration. So basically, if you do like a greedy thing, you find the best matching from each region to the target using whatever criterion you use, you're gonna get something really wrong. So this basically is something you get. But if you use the iteration method that we propose, after a few iterations, you can get a much more accurate kind of matching result. So that's the final result. And so, I mean, you may wonder why I show two of them. So the upper level and this kind of the bottom one. So in fact, the first one we use, because it's a linear program, right? Everything is, you get the floating point numbers in there. So the top one, basically, we do a hard rounding. We use a threshold to round it to get a binary kind of result. And the bottom one, we do a linear combination. So as you can see, the result is quite similar. So if you do hard rounding and do linear combination, so in fact, that means that the result is quite close to like 0-1 solution. So it's a good one. It's a good solution in here. And another thing you can see that is that when we do this kind of proposal thing, so basically the energy function is keep on going low, and it's becoming better and better result. But some middle result you can see is very wrong. So even though the energy keep going on, kind of going low and lower, but if it's not the real matching, and it could be very wrong result. So that means this kind of global optimization really helps. You need to find a global optimum instead of something in the middle. Something in the middle is, in fact, could be very wrong. And also how it works is a little bit surprising in here. So it doesn't look like it's approximated the target and gradually refined. In fact, it could go very widely kind of different and then finally get the target. So that's something kind of I didn't expect at the beginning. So there's another example that shows how it works maybe for a little bit kind of articulated object, a human body in here. So this is a template, and this is target. I purposely put it in, there's a large rotation in there. And then we do this kind of matching. As you can see, this is the first matching, and it also doesn't work very well. But if you do an iteration in here, and after a little while, and we just get a very good matching in the end. And in fact, there's a little bit, the arm, it moves a little bit. So it's not a big articulation, but a little bit. So it works for human being if there's a small deformation. So the complexity comparison of this decomposition method with the direct solution method, in fact, the improvement is quite big. So if you don't do the decomposition using this tree method to solve it, and you're going to get the complexity increase like that. So with the problem size become bigger, and the complexity is kind of very quickly can become very high. And so it means you cannot solve anything really big. But our method is kind of very flat kind of surface. So that means you can solve something much bigger than using the direct solution. And we do some comparison with some other previous methods. So in fact, that one is the proposed methods. That's A is the template. I mean, that's the matching result, our method. And there's some others, I mean, some other methods. In fact, you can see there's the comparison. The method could, if it doesn't match, in fact, it could get a very wrong result in there, because this the feature is very weak. So you need a very strong way to find the global solution, global optimal solution in there. So our methods like a 90% kind of chance to get the correct matching, and some others, in fact, is become much worse. In fact, this one is the first method that we talk about at the first part of the talk, and in fact, in here is very bad. The reason it's bad is we do this kind of lower convex Hall, and in fact, it's something not very desirable, because the feature is bad. If you do lower convex Hall, you're going to get a very flat surface in there. So that means all the kind of the details are lost. And if you optimize, you get nothing in there. So the lower convex Hall is a good optimization method if the feature is not too bad. But for these kind of very big features, you need something better than that. And there's another one. So you can see method like 90%, 91%, and other methods, the best is 73 percent accuracy matching. So it's a quite big improvement. In fact, there is some ground truth matching using the points that we compare in the paper, but I didn't show it here. So we also shows the great improvement comparing with some other methods. So there are some videos I show. So in fact, one application that we think this thing will be useful is like for human, like a human pose or something. So because of these regions, so probably it's going to kind of correspond to the arm, the head, and the torso or something. So it's going to help us to, I mean, to track the person and to understand how this movement is. I mean, the reason, in fact, we use this kind of, it's not articulated model, it's a deformable model to do this articulation. It works because the region is big. So the whole arm is a region. So basically, there's no articulation for the model itself. But if they split into like several parts, it may not work for that case. So, I mean, this method still has limitations. So if you look at this mouse, this video closer, you can see there are quite some errors. And the errors itself is one is related to the features itself. If the feature is weak, so and also also that yeah. So this is the feature itself. I think is the big thing. So this model. I mean, even though the model is strong, but if the feature is very bad, then you still cannot get any kind of good result from there. And this method is in fact useful for not only for the same object. So in fact, we use it for like matching faces, matching like the leaves or the back of the car or something. So in fact, for the face, we use one person's face to match all the other faces, like 400 faces in there. So you get quite accurate matching for the eye, the nose, and the mouth, everything. So it's a deformable, so you get a quite accurate alignment for that.
Object to a different object and see what kind of result it will get?
In fact, we did. We also let me show you some other applications in here. So like we do like action recognition. We can use this kind of matching. So in here, basically, you use one person's movement to match another person's movement. So if the feature is kind of object independent, then it works. So in here, basically, we use something like the trajectory. So if you move everything on the body, the points are going to plot some trajectory in the space, time, space, this kind of through the video. So this kind of trajectory, the shape is quite consistent, even though the person changes. For example, this guy, there's a man here and there's a woman in here, and they do the same kind of action, and you can see that in fact it's quite similar, and no matter who is going to do this and that kind of thing. So and we use this kind of thing. One application probably you can, if you want to search for some specific action in some video. So this is a broadcasting video we recorded, and for golf game, and we wanted. Usually we are interested in some kind of event. So for example, we are interested in the swing action. So we want to skip everything else. We just use one kind of template. It goes through the very hours-long video. We just localize all these kind of instances. And this basically all the shots in here is the thing that we localize. It's not totally accurate. You can see that there's something quite weird. There's a face in there. The reason it happens is that we don't really have any kind of semantic kind of meaning in here. Basically, we just match features. And for some reasons, that face is thought to be similar to that kind of thing. So, but this thing, for this application, it's like 70% of kind of accuracy for this. If you choose the recall precision, draw that point, and it's like 70% or something. So it's not too bad. You find a lot of them in there. But there's still a lot of things to do for that kind of thing. And this is kind of the application that we did is for sports data set, like 5,000 images of this baseball image data set. We try to discover what kind of actions are most common in there. So we use this kind of matching method to compare each pair of the images. And then we have the similarity distance between each two pair. And then we can do a clustering based on this kind of similarity matrix in there. And we find, okay, there's a face. There are a lot of faces in there, in fact. So that's thought to be kind of the big cluster in there. And there's some kind of throwing action. There's, you can see there are a lot of this kind of throwing. There's some other poses. And there's some kind of, oh yeah, they are the images, right? And indeed we can do something. Probably this only works for this kind of professional sports images because they may take very similar kind of events, all the time. So they choose that specific kind of pose to capture the image. But if you amateur images may not have this kind of pattern. So, but it's something interesting. We can do this automatically. All right. So that's there's some two main themes that I talk about for this how to discover the structure. I'm going to talk about some other applications, and they're maybe not kind of specific kind of common theme in there, but we use something we call the regression and branch bound. So there's some kind of integer kind of optimization problem. We want to find basically the like a 0-1 solution in there, but we can't we have to somehow relax them, and we do something like efficient exhaustive search using branch and bound. So that's the kind of thing we do in here. So the first application we do is tracking. So before, maybe let me show you some video in here. Usually the tracking method, one way is we can do DP, because each frame we can detect a lot of candidates in there. And what you need to do is you just link all these detection candidates and to make it smooth through this time. So that's basically the trick method. But if you do that for each single object, you're going to get a lot of problems. So basically, that's the dynamic programming, sequential dynamic programming method. You can see the identity that 0, 1, 2 sometimes is assigned to the same person. Multiple labels assigned to the same person, because in that, if you do this kind of DP for each of them, you don't have any kind of don't have any kind of coupling between the peoples. So you don't know that person already got the ID, so you don't know you shouldn't assign another ID to it. But our post method basically do everything together, to all the people tracking together. You can avoid that kind of situation there. Okay, so what we do is, in fact, the model is in fact multiple shortest paths. So each of the shortest paths you can do a dynamic programming, right? But if you run each of them, you don't have the coupling. So okay, let's link them together, and there's some coupling there. So basically, if you detect some object in some region, so the surrounding very close region, you shouldn't have another object in there. So if it's in there, this should be occluded. So basically, we have a kind of special occlusion kind of state in there. So that's basically the model. And unfortunately, this thing cannot be solved directly using a kind of dynamic programming or something. But we can still do a approximation, like a linear thing, and then we do some rounding, and hopefully we can get not too bad result. And in fact, it works quite well. So there's some other videos I can show you so how the result could be. So this squash video is a bit, in fact, it's quite challenging, because there are like 4 players, and there's the same team players have the same clothing, almost the same clothing. So it's quite hard. But if you look closely, this video in fact has ID switching almost at the end. So it's not perfect, and that's still a hard problem to deal with. So our problem cannot solve that kind of ID switching. We still cannot solve that problem. So we need some other information, and probably can solve them. Okay, so that's for the tracking is useful. And another set of applications that we do is like a human pose. So basically, we want to detect a person in the image. We want to find where the head is, where the torso is, and where the legs are. And so the model I use here is I treat it as a jigsaw puzzle problem. So basically, I give you a bunch of rectangles. So some rectangle represent is a torso, and some others represent is arm and leg. So what I want to do is I want you to put all these rectangles on the image so that you cover the target as much as possible. And also they link together, become a human body linkage. So that's basically the idea. So essentially, what we need for this method, you roughly need to have a foreground segmentation in there. So probably you can do like a background subtraction, and you get to the foreground. So for example, you do a background subtraction, you can roughly get to the foreground. And after you get that, and you can just put rectangles on top of that, and try to get a human body shape. So essentially, this is kind of find the best configuration of all these body rectangles. And so the name we call this model is kind of max covering, because we try to cover the foreground as much as possible. And also, it should be consistent, because it's a human body model. So we call it consistent max cover. Unfortunately, this thing can also be done using this branch and bound thing. So if you formalize it into some kind of optimization, you can relax it and get the lower bound somehow, and you can do a branch and bound and get the result. And it turns out this method works better than the single tree method. So let me show you some comparison results. If you can somehow get the foreground out, because we need this roughly foreground in there. Okay. The better the foreground you get, the better the result will be. But this method doesn't need totally accurate foreground. It just need roughly get foreground. So the first row and the third row shows the previous method is called the pictorial structure method. So basically you use a tree to represent the human body. The tree method has a problem, it's called double counting. So because there's no coupling between two arms and two legs, and very often, sometimes you're going to lose detection of one leg. So because you don't know there's a leg in there, so you detect both of the legs in there. But our method, in fact, because we try to cover the foreground, we know this part should be covered, so the leg should go there. So we can get everything in there. So, potentially it will get, because we use more information, so we can get better result. But the model is not tree anymore, so it's a global thing, so we have to kind of solve the problem much more efficiently than tree method. All right, so this is another recent work that we did. So for the human pose, so instead of detecting all these rectangles in there, we detect the regions. So the motivation we want to do this is, if you download the image from the internet, in fact, you don't really know the scale of the target. And all the previous is kind of rectangle body part region detection method needs to know the rough size of the target. So like 100 pixel tall, 200 pixel tall, something. But if you download the image, how do you know how tall the target is? And so the goal basically is, if you download the image, if you know probably there's a person in there, we want to somehow get roughly the torso, the leg, and the arm, the regions. And so in this model, basically we get the regions and we use the relative size of all these regions. So we don't really need to know the size of the target. So we can still get the right kind of configuration and detect the person's pose. And in here, basically the idea is we detect a lot of proposals. We call the region proposals. In fact, this Derek Cohen has a paper, and we use his method to detect all these object class independent proposals. It's a bunch of regions, looks like object. And in here, basically, we detect all the body parts. Some regions look like body parts. And we put them together, and we assemble them into a human body. So that's the basic idea. And also, we use this branch and bound thing to solve the problem in here. Okay, so another kind of application that we deal with for this human body tracking is we hope we can detect the hands and the head and the feet, and this we call the key points in these sports videos. Turns out this is a very challenging problem. As you can see, if you extract the frames from these videos, you're going to get a lot of blur because the movement is really fast. Of all this gymnastic movement is quite fast, so you got a lot of blur. And the blur is a big trouble for if you want to detect the rectangle body parts in there. So in here, we use a different model. We call it the walk model. So instead of using these very big features, we use the pixels level features. So it's like you start from the head, and if you walk on the image, you follow some pattern, and you go through some kind of track, and you can go to the key points, so like the hand, the feet, or something. So that's basically the model we have. And in fact, we have some other tricks to make sure this model is resistant to the scale change. We can make the walk a little bit longer, could be shorter, and it can articulate somehow. So you don't need many templates. You just need one, and you can achieve all these kind of properties at the same time. So this is some examples that shows how this thing works. So okay, in fact, there's some videos I'll show you. So we use the dot to represent all this kind of the hand, the feet, or something, and even though some of the object could be it's not a human person subject. It's like a fish or something. So basically, you can detect any kind of the point that you're interested on some object. If this object has some articulation, so this method can deal with that kind of thing. And also, it can handle this a little bit kind of scale changes and even the camera angle change, because we do this for each single frame. So you don't need to worry about the camera angle change. You can still track the target in these kind of videos. It's not 100% accurate. So there's still quite some errors in there. but roughly you get the movement of the target, and so we think it's quite useful for like action recognition or kind of understand the performance of the target subject or something. So it should be sufficient for that kind of purpose. And also we compare this method with some other like a previous like a pictorial structure method. In fact, the proposed method works much better. So one reason is that blur thing, and the previous method doesn't work well for that. And also the previous method usually has a hard time to deal with the rotation, the scale, this kind of thing. But our proposed method can handle this kind of thing very nicely. All right, so there's another application also for the human movement. So in this case, we want to somehow extract the foreground from the background. In fact, there are some previous tools we can use. For example, this in Adobe After Effects, there's a tool called rotor brush. So if you label one region in a single image, and then the software basically tracks through the video and find all the same regions in the future frames. But this method has kind of the drifting problem. So you have to basically sit there and look at the result. If the result drifts a little bit, you have to somehow modify the result a little bit, and hopefully you can track the long video frames. So this result basically show you. And sometimes it doesn't work at all. For example, for this video, there's some camera angle change. So there's no continuation for the motion. So in that case, it doesn't work. So we want to somehow handle this. So probably there's a method we can track the object, and even there's some kind of camera angle changes or something, we can still kind of find the object. So this is basically what we propose in here. So the basic idea in here is we do a partition first. We partition them into superpixels, and then we group the superpixel together, and so that the region that you find looks like the object you try to follow. And this method is kind of, you don't worry about the motion continuity because we deal with each single frame. And also there's a good property for this method is that there's a guarantee that the region you find is always connected. And in fact, it's a hard thing to do, but it's very important because it's very likely that you find two disconnected regions you can make, and the total appearance looks like the target, but in fact, in many cases, it won't be the real target. So this is a very strong constraint in here. So we have to somehow solve that using something like the cutting plane method. So basically, you keep on putting the cutting planes in there if the result is not connected. In fact, this shows how this thing works. So for example, that's the first image is a kind of the template. That's the object you want to look for in all the video frames. And then given the second video frame, how do you find this target? So basically, the method solves first the segmentation. So that's the second row, the first image. That's the segmentation you find. It's not connected. You can see this. The color histogram, in fact, match perfectly, but it's not connected. The result is pretty bad. So what you want to do is, okay, let's put some constraints in there to make sure that the result should be connected. So basically, we keep on putting these kind of cutting planes. And the result improves gradually, and in the end, it's like that. And it's a connected region, and it finds the target very well. So in fact, the object in fact size can change too. So what we want to do is you can do like everything together. So like you can make the object the scale invariant, and at the same time you want to connect it or something. So yeah, in fact, our paper shows indeed we can do that. In fact, it's much faster than if you do that separately. Yeah, there are some comparisons. And that yellow box, in fact, our method. We try a bunch of different videos, and there's some other methods I showed here. I didn't show the name, but I just want to show you it could be quite wrong because in this method, we don't really know the background information. What we know is basically the foreground information. That, in fact, makes the problem much harder to deal with. Okay, so there are some videos that show the result in here. So for all these kind of sports videos in here, you can see the background effect change a lot because the object moves from one scene to the other, and the background information is not reliable. So it means you cannot do like the foreground information, the background information, like do a graph cut or something. It won't work for this case. So basically, you have to somehow make sure the foreground has some kind of property, like the shape or something, and then do something. And in here, you can see. So this method, in fact, works even there's like a motion discontinuity. I mean, there's some errors. Some of the errors, in fact, is due to this superpixel segmentation. Is errorly kind of link the two parts that shouldn't be connected, and that caused some errors in there. But still, I mean, the proposed method can deal with kind of the size of the channel or something. So it's quite reliable for these kind of applications. So apart from this human detection, in fact, it's this kind of the energy minimization method is a global way to minimize the energy function. In fact, it could be used for other things. So for instance, here what we do is we want to detect the cuboid objects using connect images, RGBD images. So basically you have color images and also the depth images. And how do you detect all these rectangle, these cuboid things in the indoor scenes? So basically all these kind of cuboids, they give you some kind of the candidates for the further recognition or something. So so this show is, in fact, if you don't use the 3D information in there, and you're going to get something like, so for example, you look at this, and this table is not detected at all. So this show basically is, if you use the 3D thing, and if you do the cuboid detection, you can do much better results if you compare these two rows. And in fact, the basic idea of this method is still very similar to the previous one that we talked about. We formalize the thing as some kind of, we formalize them as some kind of minimization problem. And we try to find a criterion that if you minimize it, then it satisfies that all the constraints, something. And then you just need to somehow find the structure and then solve it efficiently. So in here, we do this relaxation, branch and bound. And turns out it works well, and it's quite fast. So, okay, in fact, here's a summary. We want to about this global thing. So global method, I mean, looks like it's more complex than the local methods. But in fact, there are a lot of structures we can use in them. So if we look closely at all these kind of problems, the global models, and if we can find the specific structure, we can make it really fast, and sometimes even faster than the greedy methods. So it doesn't mean that the model is very complex. It's bad. In fact, sometimes it's good. It's because it's more accurate, and you have more control for the quality of the result. And so that's we want this kind of the more accurate models. And but we can tweak the model a little bit and to make it suitable to be efficiently solved. So that's something. In fact, it could be applied to many different kind of applications. In fact, I only touched the very surface up to now. So I do different applications, but there are many others we can do using these kind of global models. So for example, the human pose, I do like a 2D thing, like the 3D pose, and also even for some very different applications like computational photography. So there are many problems. For example, if you want to reconstruct some kind of image in there, or the 3D models, so this kind of reconstruction problem usually can be formulated as this kind of optimization problem. So this kind of framework is applicable to all these kind of things. So there are many things we can do, and so if we, if we formulate some kind of suitable models, and hopefully we can solve some vision problems easily, and also we can get reliable results. So that's something we can do. I hope I can do in the future. And yeah, that's it. And thank you. Thank you.